Thank you very much to Mr. Lab Research for organizing both this webinar series and also the very informative seminar series that we had at the ENC this year. So today I'd like to tell you about the NMReady 60 MHz Benchtop Spectrometer that's made by my company, Nanalysis Corporation, and also to speak about some applications that exhibit the NMReady's capabilities. So our company was established in Alberta in Calgary, Canada in 2009, and our mission was to provide NMR in an affordable, easy-to-use benchtop package for teaching, reaction monitoring, and routine research tasks. Our first product was introduced in late 2012, and now the family includes an upgraded NMReady E and also an enhanced functionality multi-nuclear NMReady 60 Pro that will be shipping in mid to late summer. So some basic physical data and information about the user interface. The instrument is about 53 pounds, about 25 kilograms, and it features a shielded 1.4 Tesla hybrid Halbach magnet that takes proton NMR spectra at 60 megahertz. It also has a touchscreen operator interface. The touchscreen interface starts with a Go screen, a basic Go screen, and also includes various screens for phasing data or for integration and peak picking, for instrument status updates, and also file management capabilities and so on. And it also features versatile connectivity. So on the side of the instrument you'll see connections for Ethernet and for HDMI cables and also for USB drives. It can be connected to an Ethernet LAN, for example, or to printers and so on. It also has a hole at the bottom and features a flow cell configuration that we're developing in collaboration with the Fraunhofer Institute for Chemical Technology. Here are some experiments and applications. It does basic routine NMR spectroscopy, and so, for example, it does one-pulse proton and fluorine-19 NMR at 60 megahertz and at 56.5 megahertz. Here are spectra of ibuprofen, and importantly, you can see all of the chemical shifts and all of the J-couplings in this small molecule. This spectrum here was taken in about a minute. This fluorine spectrum was also taken in about a minute, and here you can see all of the intimate detail of the J-couplings, the fluorine-fluorine J-couplings in this molecule. You can also do a basic mag-mode COSY, in this case on diethyl phthalate. And here you can see the cross peaks indicating the coupling of the protons in this ethyl group. You can also do relaxation experiments. You can do T1 curves or T2 curves, and this data here were taken on aqueous manganese ions at various concentrations as part of a relaxivity study. So I'd like to talk about two particular applications briefly, and then I'm going to move on to another series of applications mostly surrounding teaching in the in the undergraduate chemistry laboratory. So the first application I'll talk about is copolymer characterization, and then I'll talk about edible oil adulteration analysis, and then after that I'll talk about the teaching applications. So here's a spectrum of a sample containing polystyrene polybutadiene block copolymers. These polymers feature monomers that are linked in blocks, in this case styrene blocks and then butadiene blocks. And the butadiene blocks can come in two ways. The result of a 1,4 addition, which produces an internal double bond, as you see here in the molecule on the left, and a 1,2 addition, which produces a terminal double bond here. And all of the features, that is the styrene resonances and the two different kinds of vinyl resonances, appear in the spectrum and can be quantified. So one can assess the degree of internal versus terminal double bond addition in the polymer based on reaction conditions, for example, and also quantify styrene versus butadiene. A look at the quantitative data in comparison to the same spectra run on a 400 megahertz spectrometer shows that the quantitative data can be quite good. Here we take the integrals of those aromatic peaks and also of the olefinic peaks and produce a percent polystyrene, and the agreement is quite good. In a separate study having to do with polystyrene, polyisobutene polymers, the match was even better. Okay, for the next application, I want to talk about olive oil adulteration. It turns out that olive oil sometimes is adulterated with less expensive oils like soybean oil. Olive oil is very important nutritionally because of its monounsaturated fatty acid content. It's mostly monounsaturated fatty acids with some polyunsaturated fatty acids and saturated fatty acids. Soybean oil isn't so much in monounsaturated fatty acid content, and it's also substantially less expensive. Here you can see the unsaturated fatty acids, both the polyunsaturated acids and also the monounsaturated oleic acid molecule. And the important distinguishing spectroscopic feature in these molecules here is what we call the bisallylic protons. Those are those protons here on these carbon atoms that are connected to two allyl moieties. And they're very prevalent in the polyunsaturated fats and absent in the monounsaturated fat. Here are some spectra of pure olive oil, pure soybean oil, and then olive oil mixed with soybean oil in various concentrations. And you can see a principal difference in the spectroscopic features are, again, this peak in the bisallylic region. So if we monitor the relative integral value of the bisallylic region, we can construct a calibration curve for soy-doped olive oil. And here you can see that curve. And the spectral response is actually quite linear in the percent bisallylic concentration. Now, each one of these samples was run 3 times. And here I show an example of the quantitative repeatability achievable with the NMReady spectrometer. You can see that the 3 spectra overlay each other quite well, and that the integrals here are, in fact, very reproducible. Okay, another important function of quantitative studies is the long-term stability of the spectra. And so we've taken 30 overlaid single-scan spectra of 50% isopropanol. And here's the spectrum right here showing 3 different multiplets. You have the hydroxyl, you have the methine resonance, which is a septet, and you have a doublet, which is the methyl group. And so we looked at the integrals of this methine resonance here, and here it's shown expanded at 3.9 ppm. And these are 30 spectra all laid on top of one another, taken over 28 hours. And the standard deviation in the integral of this septet doesn't deviate by more than about 0.004, that is about 0.4% over the whole time that the spectra were taken. Okay, I want to switch gears now to the main part of my talk, which is to talk about the applications of NMReady in the teaching laboratory. Now, the idea of using Benchtop NMR for large classes of elementary organic chemistry students is very appealing, and in fact we've produced a number of experiments and made them available on our website. For example, you do an aldol condensation, or you do a synthesis of aspirin, typical things you might do in an undergraduate organic chemistry laboratory that can be enhanced with a Benchtop NMR experience. That's a kind of obvious application of an NMR spectrometer, that is to say, just in support of synthetic studies. But what I really want to talk about today are some different kinds of studies that are particular to an advanced lab or to a physical chemistry laboratory. Okay. The first one is preparation of biodiesel, the synthesis of biodiesel, and its monitoring of this transesterification reaction. So biodiesel takes lipids and transesterifies them with methanol, for example, in basic solution. And what you end up with is this methyl ester. And so we can look at the spectroscopic changes associated with this chemistry, and in particular, the disappearance of glyceride resonances and the appearance of a methyl ester resonance. Now here's a procedure adapted from the Journal of Chemical Education, and this is a procedure that does not include spectroscopy, and in particular you synthesize the biodiesel, and at the very end the procedure calls for a measurement of the synthesized biodiesel's melting point and for other physical properties, for example, refractive index and optical rotation. Now, but when people do chemistry in the real world, it's very, very common to just run NMR spectra. And so again, you can adapt this experiment to study with Benchtop NMR. And the adaptation would be just to prepare 10 NMR tubes by adding half a milliliter of deuterated chloroform to each one, weigh out your feedstock into a beaker, add a stirring bar, perform the reaction in deuterated methanol, add your base to the reaction mixture and stir it, and then take 0.1 milliliter aliquots of the reaction mixture and add each one to an NMR tube as the reaction proceeds. That is, taking a 4-scan NMR spectrum and heating and stirring the reaction mixture for 45 minutes, taking about 10 aliquots every 3 to 5 minutes. Here's the result, and you can see in this stack plot some spectral features that disappear and some that appear. And in particular, there is a glyceride which disappears as the reaction proceeds at about 4.2 ppm, and then a methyl ester resonance that grows in as the reaction proceeds. If you look at the integrations and plot them, you can do first-order rate plots. Here we see the exponential decrease of the reactant and the exponential increase of the product. And one could make an Arrhenius plot of the log of the concentration, which is to say the log of the integration, and then find a first-order rate constant. In this case, it's 0.005 per second. And the data look quite linear, indicating a first-order kinetics. Okay, I'm going to switch gears now to another type of experiment. And here it's a physical chemistry or general chemistry experiment in which we do an NMR determination of the pKa, the acid dissociation constant, or rather its negative logarithm, in substituted pyridines. So here we see a series of substituted pyridines that differ in their R groups that are attached to this aromatic ring. And pyridine is known to be a base. This nitrogen right here has a lone pair which can attract a proton from solution, and so we have an acid-base equilibrium. And the two species, the acid and the base conjugate pair, have two different spectra. If you look at the aromatic region between about 7 ppm and about 9 ppm, here we have in pyridine, this R group is just a hydrogen atom, and so we have ortho, meta, and para resonances within the region, and those shift depending on whether you're in the conjugate base state or the conjugate acid state. Now there's another resonance here, which is water. Of course, it's residual water, but there's also another reagent we put in here, which is tetramethyl ammonium iodide, which is used as a chemical shift reference. Okay, so what we'd like to do is we would like to take concentrations of these species and then put them into the Henderson-Hasselbalch equation, or this mass action expression here, in order to measure the acid ionization constant. Now, in fast chemical exchange, we have an average chemical shift, which is a function of the chemical shift of the pure base and the chemical shift of the pure acid scaled by their mole fractions. You can invert this equation and therefore calculate the mole fractions and therefore the concentrations if you can measure the chemical shifts. All right. In the procedure, you obtain an unknown nitrogen base from a TA. Again, this is done as in a laboratory class in groups of 2 to 4 people. You prepare base and acid solutions in D2O, and in a wide-mouth Erlenmeyer flask, you combine the reagents, including the tetramethyl iodide and the base, and stir it. If the solution is greater than 1 in its pH, you add HCl stock solution until you bring the pH down. And then you transfer 0.7 milliliter aliquots to an NMR tube. You measure the proton NMR spectrum for each sample using 2-minute scans, and then you raise the pH by adding potassium hydroxide solution, measuring the proton NMR spectrum about every 0.5 to 1 pH units until the pH comes up to about 4, and then samples more slowly every 0.2 pH increments or so. And this is adapted from, again, the Journal of Chemical Education. Okay, so here's what you see in the spectrum. And again, we have a peak at around 3.2 ppm, which is the chemical shift reference, the tetramethylammonium iodide. And then you see in the aromatic region a sudden shift in the chemical shifts as you go through the equivalence point. The data are tabulated here, corrected for chemical shift, and we then can plot the chemical shift versus pH to inspect the graph to estimate the pKa from the apparent equivalence point, which in this case is at about 5.1. You can also do this a bit more precisely by plotting the logarithm of the ratios of the mole fractions of the base to the acid versus pH, and then fit that to a line according to the Henderson-Hasselbalch equation. Okay, discussion in context with the students. The students share pKa values from their variously substituted picolines and lutadines, as shown here. And these variants of pyridine can be more complex substituted pyridines and so on. And one can rationalize the trends in acid-base strengths on the basis of things like resonance effects, electron donor acceptor behavior of the substituents, and so on that they've learned in lecture. Okay, I want to shift gears a little bit, but remain in the theme of acid-base chemistry here and talk a little bit about some work we're doing to develop another experiment for the NMReady. And in this case, we want to look at pH dependence of the J couplings in glycine. Here I show glycine, and it's known that glycine exists in a molecular form, shown on the left, and also in a zwitterionic form, which is shown on the right here, where the proton is transferred from the carboxylate moiety over to this more basic amine moiety. But what we're going to do is we're going to look at the J couplings in this glycine molecule in the NMR spectra as a function of acidity of the solution, and we'd like to relate the fitted NMR parameters with ab initio calculations using the Gaussian program of its electronic structure and NMR parameters. Okay, so glycine in aqueous solution, as we've said, exists in these two forms, and it turns out that, at least in aqueous solution anyway, the equilibrium here is very strongly to the right, and so the prevalent feature, the prevalent form is this zwitterionic form. But as you change the pH to an acidic or a basic solution, you can deprotonate the molecule as a whole in base to give this ion here, this anion that is in basic solution, or you can protonate it at low pHs and see this ammonium version. Now, what we'd like to study is what happens to the J couplings in this molecule as a function of pH, and the hypothesis is that they would change. And why would that be? Well, there's the J couplings I'm talking about are the one bond J coupling here between this carbon atom, what we call the carbon C alpha, and its attached proton, and the two bond J coupling associated with this proton here and the carbonyl carbon. And the reason that this might change is because of the electronic structure of glycine. And this electronic structure is actually important in things like backbone rigidity in proteins and so on. It's known that this set of bonds here can hyperconjugate to this carbonyl moiety, okay? And also this alpha carbon moiety here is trapped in a sense between two pi systems, between the pi acceptor, which is this carbonyl carbon, and also the pi donor, which are the lone pair, either the lone pair on this nitrogen in the deprotonated form, or in the protonated form, the bonds associated with the NHs. And so what we're going to do is we're going to isotopically label the carbon atoms here so that we can see a nice strong doublet of doublets in the NMR spectrum, and so that we can fit that in Mnova. Now, the study can get quite a bit more complicated. What we're just going to show today are the NMR spectra and their fits and their relation to Gaussian calculations of those NMR parameters. But the significance of the J coupling is that it reports on the degree of S character in these sp3 hybridized bonding orbitals, because the J coupling, its most significant component in these molecules is the so-called Fermi contact interaction, which depends very strongly on the S character of the electrons that are involved in the bond. Okay, so here are the spectra, again measured on the NMReady 60 in relatively concentrated solutions, moderately concentrated solutions. There's about 20 milligrams or so in 0.7 milliliters of solvent. And you can see the spectral features most easily in the basic version. So as expected, you see a doublet of doublets, and you might think, well, gee, this coupling is very, very strong. Recall that the NMReady is operating at 60 megahertz, and so a 135 hertz J coupling shows up as a substantial number of ppm. So here's our doublet of doublets, and this large coupling here is due to the one bond J coupling, and the smaller coupling here of about 3 to 5 hertz is the two bond J coupling. Now we compare these to ab initio estimates that were made in collaboration with Dr. Len Mueller of UC Riverside, and what you can see, these are fit in Mnova, and these fits produce very, very good J coupling values. These values here from the fits are probably inaccurate to no more than about 0.2 to 0.3 hertz or so. There's a little bit of spectral overlap here in both the neutral solution and in the acid solution with this larger peak here, which is the residual protons associated with exchange of the acidic protons on the amino moiety and the carboxylate moiety with residual H2O in the deuterated water sample. And when we compare them to the Gaussian results, in Gaussian you can calculate NMR parameters, including J couplings. The agreement with the acidic case is excellent, and the agreement with the neutral and basic are not quite as good, but the trends are certainly shown very well in the electronic structure calculations. There's a bit more to the story. But I think what I'm going to do is I'm going to stop now, and if there are any questions, I can take those. In the meantime, if you'd like to learn more about the company or about the NMReady 60 family of spectrometers, you can visit us on our website. On YouTube, we have some videos that demonstrate the use of the user interface, and some testimonials from customers who've purchased and enjoyed our spectrometer. And you can also follow us on Twitter. And I'd like to thank you very much for your attention. All right, I will go ahead and open my screen and see if there are any questions. Okay. Let me figure out how I'm going to do this part. Okay, it looks like there are quite a few questions here. I will try to answer as many of them as I can. It looks like we have perhaps 3 minutes or so. And I will be with you in a moment as I scan the questions and pick one I can answer. Okay, yes, I have a couple of people have asked regarding whether there are shims. And yes, shimming on the NMReady spectrometer, there are manual shims that are available from the touchscreen interface, but there is also a automatic shimming procedure that is used. It turns out that the NMReady is quite stable, as I showed when I showed those results for isopropanol. That 28-hour spectrum, there was no shimming done. It was done at the beginning, and then it was left on for over a day without shimming. But yes, you can shim. Let's see. We have a question regarding kinetics. Can you run kinetics automatically? And the answer there is we are coming out with a software package that will automate that procedure. The data that were shown here were just collected in a minute-by-minute basis by the user. But yes, we have in an enhanced software package, we have an automated kinetics capability. I have another question here regarding acrylic monomers in polymers, and the question is, would you be able to quantify different acrylic monomers, such as MAA and BA, accurately within a copolymer? And the answer is yes. Certainly, the degree to which you can accurately quantify monomers is going to have to do with the spectral overlap. And as you saw with our extraction of data in the glycine experiment, it is possible with tools like Mnova to accurately quantify those spectra. It's hard to say. It would depend upon what conditions you ran your experiment under. The last question I can answer, it looks like we're running out of time here, regards the flow cell. And the question is the flow cell an accessory, or will we need a dedicated instrument for that purpose? And the answer I have for you is the NMReady, as it stands, is ready to accommodate it as an attachment, and that attachment system is going to be available later in the year. Okay, that's all we really have time for right now. It looks like there are quite a few more questions. I wish I could answer all of them. If you're interested, you can send email and get in touch with us at our website. I'm going to go ahead and thank you again for your attention, and thank the folks at Mestre Lab Research for inviting me to speak, both here at the ENC, and say good day. Thank you.